All right, let's go then. Welcome to week 3. Are you having fun learning decision trees and mining click streams? Yes, I see from your smiles that you are. So maybe the next project needs to be harder, so you know what data mining really is like. In the meantime, today we're going to talk about rule induction, another major area of machine learning. And in fact, we already talked a little bit about rule induction last week, right? Because the last thing that we saw was how to turn decision trees into sets of rules, and how nice sets of rules are because they can be very compact and easy to understand. But here's a question that may have occurred to some of you. If what we're going to learn at the end of the day is a set of rules, right? Why are we doing it by way of learning a decision tree? Couldn't we just learn the rules directly? Wouldn't that be a better way? Well, the reason we learn both is that, they have their pros and cons. But let's look today at how we can actually learn rules directly. And in fact, we're not going to stop at that. We're also going to see how we can learn much more powerful rules than the decision trees that we saw last time. When we started talking about machine learning, I said that machine learning is, learning programs from data. But the programs that we've seen so far are very limited, right? The decision tree is just a set of, basically nested if then else statements. Today we're actually going to see how you can learn full-blown programs. Okay? So last week we got down the basics, but this week we're really going to, climb into the stratosphere. So fasten your seatbelts. Okay? All right. So as usual, let us first think about what rules are and what kind of learning algorithms do we use for learning rules. So first of all, rules are very popular, and for a reason that's easy to understand, right? Rules are probably the most easily comprehensible thing that you could mine. They're even simpler than a decision tree. It's just a bunch of statements that you can actually read in English and they make sense, right? In fact, I don't know if you've had the experience of having credit card application rejected, and then there's a piece of text that says, your application was rejected because you haven't lived long enough at your address and your employer blah blah, right? The thing that you should hate there is the rule induction algorithm that produced that, right? It should know more. But nevertheless, it's actually something that you can put down in writing and people can just read it without any expertise. Okay? So this is one of the main advantages of rule sets, is that they're very understandable and often very compact. Okay? Excuse me. Like decision trees, rule sets are a variable size representation. If I have more data, I can learn more rules, and they can be longer. They can be more detailed. They can have more preconditions. They're also deterministic, and they also can have both discrete and continuous parameters. So the discrete parameters are the choices of tests that you put in the rule. And the continuous parameters can be things like the thresholds for tests that you have on continuous attributes, or things like the probability of the class given the attributes, right? If this email has these words in it, then it is spam with some probability, for example. Okay. Learning algorithms for rule sets, like decision trees, are also constructive search, right? How do we learn a set of rules? Well, the natural way to do it is to learn one rule at a time, right? And the natural way to learn one rule is to learn one antecedent at a time, and that's what we're going to do. We're going to construct the rule set step by step. Most rule induction algorithms are eager, and they batch, meaning that we have all the data at training time, and then we do as much with that data at training time. We learn a model that then hopefully is quick to apply. Okay. Again, there's exceptions to this. There's online rule learning algorithms. There's lazy algorithms, but for the most part, rule induction is an eager and batch process. Okay. Any questions so far? All right, so first of all, what is a set of rules, right? What is the hypothesis space that we're going to be working in during this class? Well, a rule, right, is just what you probably already think it is. It's just a set of tests. Each one is of the form, this variable is equal to this value, if the variables are discrete, like, for example, the color of the car is red. Or this variable is less than or equal to some value, or greater than or equal to some value if you're talking about a numeric value, like, the temperature today is above 60 degrees, for example. Okay? These v's and these x's are values and are attributes and values that appear in the training data. Okay? And it's out of those that we're going to build up the rules. Okay? And then what a rule says is things like, for example, if the variable x1 has the value sunny, and the variable x2 has a value less than 75%, then the class is yes, meaning we are going to play tennis. Okay? So this is one rule. A set of rules is just a disjunction of rules. Okay? So let us assume for the moment that we're just going to learn a concept, right? So we're just trying to learn something binary, right? Is this a car that I want to buy or is it not, right? Does this patient have pneumonia or does she not? Okay? So and a little bit later we'll talk about learning with multiple classes. But when we're learning rules for one class, the simplest thing to do is to just have the model for the whole class to just be a disjunction of the individual preconditions, right? So the email is spam if it meets these preconditions or it meets those. Okay. So at the end, what you have is a DNF, a disjunctive normal form defining the rule, defining the concept. So for example, we could have these three rules. If x1 is sunny and x2 is less than 75%, then yes. If x1 is overcast, then yes. If x1 is rain and x3 is less than 20, then yes. Okay. Notice there are no rules here saying no. The reason there are no rules here saying no is that the answer is no if none of the rules match. Okay. So I have only rules for the positive class, and then if none of the rules fire, then by default I just assume that the class is no. Okay. There are other ways to do things, but this is the simplest one, and it's the one that we're going to focus on for the moment. Okay? So, question number one. So how do rules relate to decision trees? Right? We touched on this last time. Right? What is the relationship between a decision tree and the set of rules? Okay? Does anybody remember?
Different representation of the same concept.
Exactly.
You can build rules from decision tree.
Right. So I can take a decision tree and convert it to a set of rules. Right? How do I do that?
Every leaf is a rule.
Right. Every leaf is a rule, and the conditions on that rule are the conditions on the path to that leaf. Okay. So in particular, the rules that we just saw here, right, are what you get from this decision tree, which is the one that we've been playing with all along, or something close to it. Okay. So going from decision trees to rules is easy. Okay. But now the next question is, what about going from rules to decision trees? Actually, let me hide this slide for just a moment, because temptation can be hard to resist. Right? And first of all, can we always, so we know that we can always translate the decision tree into an equivalent set of rules. Right? Is the inverse also true? Can I always translate a set of rules? Let's say, in a Boolean domain, the variables are Boolean, the class is Boolean. Can I always translate a set of rules into an equivalent decision tree? Yes or no? Yes? Anybody want to say no?
No.
Okay, so we have yeses and no. So let's hear the case for the yes.
If it's going to represent a Boolean function, then there must be a way to represent it as a decision tree. They can represent any Boolean function with a decision tree.
Right, remember we saw a long time ago, all those weeks ago, right, that you can represent any Boolean function with a decision tree, right? So what do the no's have to say? Somebody remotely was saying no.
So, what if you can't really find something to be the root of the tree? Like you have multiple rules. I don't know how to describe it too well, but I think the idea is like, for instance, how we have Outlook as the root in the decision tree. If you created a set of rules, then you could actually minimize it to the point where something like Outlook is no longer relevant.
Very good, actually. So this is a real problem. So what you're saying is that you can't see how you would do it, right? You want to say something?
Yeah, and also I remember we talked about pruning, and when you prune it, with rules you could actually prune a rule, but still not remove the node. So
No, I agree, but notice, for the moment we're not talking about learning algorithms, right? We're just talking about the representation.
Right. So my point is, you could represent rules like that, which you cannot represent directly as a decision tree.
Yeah, so at heart these problems are the same, right? So let's think about this, right? So at some level we know that it must be possible. What it's not obvious is how. And we can figure out how, but this is going to have consequences, right? So the natural question is, who's going to be the root of the tree, right? So does one of the yes votes have a suggestion, right? You said it's possible, right? In theory, there's this notion of a constructive and a non-constructive proof, right? So you could have a non-constructive proof, but we can have a constructive one, yeah.
I mean, assuming these are all like disjoint variables, like you have A, B, and C, and you pivot on those. At root, you can pick a random one, say A, and at the two other levels, you pivot on both trees at B. And one of those is going to be redundant for like the no, I think, depending on the rule. And then at the third level, you have like, a total of 4 C's. They're all redundant, but you're covering every rule that you were worried about making a root.
Yeah, very good. In fact, this general idea works even if the rules do have overlap in attributes.
Right.
In fact, the overlap with attributes, kind of looks like it complicates things, but all that happens is that I already tested that value before, so I don't need to test it again. So, but let's pursue this idea, and here's a concrete example, right? Here I have 3 rules, very simple ones. x1 and x2, then y. If x3 and x4, then y. And if x5 and x6, then y. Right? Another question is, how do I build a decision tree out of this? Well, let's just pick one of them. Actually, picking any one. Clearly, the decision tree is going to depend on x1, x2, x3, x4, and x5, and x6. Right? It's going to depend on all of those. Which one of these shall we put at the root? It's not always irrelevant which one you put at the root, right? Because you could get a smaller or larger decision tree. But for the moment, let's just worry about doing this any way that we can. Okay? So let's just say that we pick the first antecedent in the first rule. Why not, right? So the first thing that we test is x1, right? And then notice that if x1 is true, right, we're going this way, right? And then obviously we need to test whether x2 is true, because that's the other antecedent in that rule, right? And if x2 is also true, then what do we know?
We win.
Then it's a yes, right? Because that rule says it's a yes, and that's that leaf over here, right? On the other hand, let's go back to the root. This is the interesting part. What happens if x1 is false? If x1 is false, then this rule doesn't fire, right? So then where are we? What do we need to do now? Does that mean that the example is false too? No, right? Because it could still be true because of one of the other rules, right? Everybody agree? The first rule failed to say yes, but well, there's still the others, and those might say yes, okay? So now what we need to do is what? As always in decision trees, this is a recursive process, right? So the first rule has failed, but now we need to do what?
You need to represent the other rules on both sides of the tree.
Exactly. So we need to test the second rule and then the third rule. And, 2 people have already alluded to what the problem is going to be, right? So let's see what the problem is. When x1 is false, right, now I need to test the second rule, which means I test x3 and then x4, right? And if x3 and x4 are both true, then I get the answer true, right? And, to keep going, if this rule is also false, right, then I have to test the last one, which means first I have to test x5 and then I test x6, and if they're both true, then the result is 1. Okay? Everybody with me so far? Now, we've captured all the yes cases, right? But we're not out of the woods yet. In fact, woods is actually an appropriate metaphor here, right? We're in a big jungle. Why are we in a big jungle? Because notice, I don't just have to test for the second rule over here, right? I also have to test for it over here, right? Because over here, right, this first rule has also failed, right? So in that case, again, I'm going to have to test the second rule. So what do we get here? We get a repetition of the same subtree that we had over there. Notice that the subtree rooted at this node and the subtree rooted at this node are the same. Right? You see what's happening here? I have to go test that subtree in every case that the first rule fails. Right? If there were 10 antecedents in the first rule, I have to do this 10 times. And then what happens when the second rule fails? In every one of those cases, I'm going to have to test the third rule. And if I had 100 rules, this would be really bad news, right? Because this means that the size of the tree is going to grow how? With the size of the rule set?
Quadratic.
Worse than quadratic. Exponential. Right? I'm going to need to look at all, in the worst case, right, I need to look at all combinations of truth values of the rules. And I need to have a subset of the tree for, true, false, false, etc., etc. Yeah.
You can share pointers though, right? Across the tree.
Oh, very good point. You cannot. Although you could learn a different model called a decision graph. In a decision graph, you can have pointers to the same thing. Okay? So in a decision graph, we would not have this problem. Right? Or at least, most of this problem would be solved. It's still not necessarily the case that the decision graph would be as compact as the set of rules, but yes, the decision graph would obviate this problem.
I see. So is that just because of the definition of a tree?
Yeah.
I see.
And the problem with the decision graph is that it's more complicated to learn a decision graph than a decision tree. So even though they're a very natural idea, for the most part, people never use decision graphs. This was tried at one point. They used decision trees. But decision trees do have this huge problem. It's called the replication problem. Because you get more and more replications of the same things as you go down. Notice that, for example, by the time you get to the end of this, you've tested x6 here, and you've tested it here, and you've tested it here, and you've tested it here. There were 4 tests of x6. And if this rule came at the end of a whole bunch of other more, instead of 4 tests, there would be 8 or 16 or 2 to the who knows what. And notice, there's nothing particularly pathological about this set of rules. It's a perfectly simple and natural set of rules. So decision trees have this very sticky problem, at least compared to decision rules, that the same concept could be exponentially larger expressed as a decision tree than expressed as a set of rules. Not always, but it can happen. Okay? So this is one significant advantage of rules over trees. This is not just a representational problem, by the way, right? Because the other thing that we saw last time was that as I grow the decision tree, I get less and less data, right? And so as I grow, notice that once I split on x1, I only have half the data points, roughly speaking, on each side. So now when I finally get to inducing these subtrees, they're being induced on a fraction of the data that I had before. So the data dwindles for learning decision trees in a way that it doesn't dwindle for learning rules, which means that we might not be able to learn something as a decision tree when we would be able to learn it as a set of rules. Okay? Any questions? Okay, but if rules are so great and trees are so bad, then why do we bother with learning decision trees? Why are decision trees the most popular, data mining method and not rules? What are the potential disadvantages of learning sets of rules or complications?
Slower at runtime?
Sorry? At runtime, yes. At runtime, decision trees are blindingly fast. Decision trees are just about the fastest thing you can have at runtime. Right? You just, go down one branch. It's all there for you. Rules, you have to match all the rules. If you have a lot of rules, that could take a long time. That could be too slow. What's another potential complication? We also saw this last time when we looked at rule post-pruning. With decision trees, you always know who's the winner because there's only one. Right? You only go down one branch. With rules, well, sure, I have all these rules, then they all fire. So what do? In this case that I have here, that doesn't happen because I only had rules for the positive class. But jumping ahead, if I had rules for multiple classes, then I have a non-obvious decision to make. Okay, these are 2 problems, but there's another one which is more subtle, but perhaps more important. Can anyone guess at what it might be? Just use your gut feeling. By the way, here's a good rule of thumb. If somebody ever asks you, what is the problem with this machine learning algorithm, you have no clue, just say overfitting. You will be right more than half the time. Okay. That footnote aside, let's go back to our question. What might be the other problem with rule induction over decision tree induction? Yeah, exactly. They're more prone to overfitting. Why would rule induction be more prone to overfitting than decision tree induction? This now is not an obvious question, but think about it for a moment. Why would we have more chances to overfit when learning rules than when learning decision trees? And therefore have to be correspondingly more careful. Yeah?
I think you're always looking at all the attributes. That's one thing.
Yeah, so that is one aspect, is that, remember, when we're learning a decision tree, we're computing information again over all values of an attribute. On one hand, this is unfortunate because it ties them together, but on the other hand, it's fortunate because it actually avoids making highly overfit decisions, at least better than with rules, right? We will see in a bit that with rules, you run a very high risk of overfitting very highly. Right? And the other way to think about this, which is more it's a more flexible representation, right? And therefore, since it's more flexible, on the one hand, that's good because you can learn more things, but on the other hand, it's bad because you run a bigger danger of overfitting, or finding some set of rules that looks good just by chance. And this is a trade-off that is always going to be present in machine learning. Okay, so we might as well get used to it, right at the outset. Okay? Questions? Very good.